to go. Yeah. So, welcome everyone. Another introduction to astronomy session. Any new members in the last month? No? Any new members? Oh yeah, welcome. New members in the last 12 months? Oh, that's great to see. Good. Because what we try to do with Introduction to Astronomy is pick a topic, have some fun by all means doing it, but try and use it as a vehicle for principles of astronomy. So that's what we're doing today. So this here is a artist's cartoon impression, obviously not to scale, but of our solar system. And you'll see over to the left there's the sun, the host star. And there's a group of 4 small rocky inner planets. And then you've got your disk of about, or your belt of about 1.4 million small rocky objects, known as the asteroid belt. Then you've got these 4 outer gas and ice giants all grouped together. And then you've got another belt of trillions of rocky icy objects, known as the Kuiper belt, which gives rise to what we call short period comets. Comets, and remember those icy objects that go around the sun, and any comet less than about 200 years to go around the sun for a complete orbit, it's called a short period comet, and they thought to come from this Kuiper belt. And you'll see the artist has drawn in here some long period comets, and they're ones that come out from called the Oort cloud, a spherical cloud of icy small objects that's been hypothesized to be about a light year out. And they're coming in there. So that's the diagram very roughly of what the solar system looks like. And today we're going to go on a visual journey. We're going to focus just on the planets and a few interesting moons along that, but the 4 inner rocky planets, the 4 outer gas ice giants, some of the moons. So we're going to have a visual journey of these planets. That's why tonight's talk is the planets and the moons of the solar system through modern eyes. We've got get some images from recent rovers and computer simulations and so on. And after the visual tour of the solar system, we're going to answer these 4 questions. Why is there a dichotomy of planets? You know, the one group, small, rocky, all inner, and then you've got that other big group in the outer parts of the solar system, much more massive and made of ice and gas. They call that a dichotomy. So why is there a dichotomy? Why is Mars a little runt of a planet? You know, that formed further out from Earth, and it makes sense. When planets form, you get the host star, which is our sun, and you get a big disk called a protoplanetary disk form around it, and the planets form within that disk. And it follows that the further you go out in an orbit out in that disk, there's more material. So why is Mars further out than Earth and it's only half the size diameter-wise? It's a runt in the litter. Why is that so? We're going to answer that. Why isn't Earth a super Earth? So Earth is yay big, but very common in other planetary systems and exoplanets, you have these rocky planets that are much bigger, up to 2 times the size of Earth. They call them super Earths, and they're really common. We don't have any here. We've got our Earth. So why isn't Earth a super Earth? So we'll answer that question. And why isn't there a planet between Mars and Jupiter instead of just a ring of rubble known as the asteroid belt? Why isn't there a planet? A planet should be sitting there. So we're going to answer those questions today. But first of all, we're going to go through a visual tour. I've split it into these 2 chapters, the visual journey through the planets and some of the more interesting moons. And then we're going to go for 3 reasons explaining the dichotomy talked about, and we'll answer those questions. So let's do the first chapter. This here is the 4 planets. That's to scale. Their sizes to scale. So you can see here there's Jupiter, Saturn, Uranus and Neptune. There's Earth, Venus, Mars and Mercury there. So that just gives you an idea of their scale. So let's have a look at their scale differences, their distances from the sun and from one another, because that's quite interesting too. And we're going to start off introducing the idea of an astronomical unit. And it's a unit, a measure of distance that you use when comparing the distance between the planets and how far they are from the sun, whereby 1 astronomical unit is by definition the distance from the sun to the Earth, which is about 150 million kilometres, and it's 1 astronomical unit. So it's quite convenient just to talk in that way, and I've just made some generalisation here, which we're going to have a look at. So first up in the order, of course, is Mercury. And Mercury sits at 1/3 AU. So in other words, it's about 50 million kilometres from the Sun. So let's have a look at Mercury. This here is an image from NASA's Messenger orbiter that was orbited Mercury from 2011 to 2015. It took 7 years for Messenger to get from Earth to Mercury. The same distance in the opposite direction, say going to Mars, same distance is only about 9 months. Any ideas why? Any takers? Why 7 years to get the same distance?
It's very difficult to get rid of kinetic energy.
Yeah. So the bottom line is you're travelling downhill. You're heading towards the Sun. Gravity is getting stronger and stronger and stronger. So if you thought, okay, let's head towards Mercury, away you go. Mercury's over there. You're not going to be able to stop. You're just going to plough into the Sun very, very quickly. So what it does a complex set of manoeuvres. It swings by the Earth again, swings by Venus, through Mercury. It's quite a process of 7 years, and it uses various flybys to brake, so to speak. And so then before it went into orbit. So Mercury is 1/3 the size of Earth, diameter-wise. Usually when they talk about comparative sizes, they're usually referring to the radius, i.e. diameter. It's about 1/3 of the size. And what's your first impression of Mercury? It looks like the moon, doesn't it? It looks highly pocked and sort of pockmarked and lots of craters and stuff, heavily cratered. Why? Why is it heavily cratered?
Burn the atmosphere.
Yeah. No, two reasons why. No geological activity. So no heat from within, internal heat coming up, driving volcanoes or tectonic plates and stuff, because normally it's all that sort of activity that covers the surface. It's a very old surface. Why hasn't it got geological activity? Because another little concept in astronomy, or just general physics, is that if something is smaller, it's got a very large surface to volume ratio, so it tends to cool off very, very quickly. So it's lost its internal heat. So it's no geological activity, so to cover up and renew surfaces. So you're seeing all the pockmarks from what they call the late heavy bombardment phase. We'll talk about that later, where the inner solar system was bombarded by loads and loads of rocky objects heading inwards and crashing into the planets. So no geological activity, so that's one reason why it's heavily cratered. The other one, it's got no atmosphere. We take for granted that little meteorites are coming towards us all the time, that our atmosphere burns a lot of them up or softens them up, so to speak. And no atmosphere, it's just so, once again, it's like the moon, just in they go and create a crater. Why doesn't it have an atmosphere? Because it's too small. The planet's too small. It doesn't have enough mass, enough gravity to hang on to a decent atmosphere. So there's just some general principles of astronomy there, of planetary science. Because it's got no atmosphere to moderate and spread its heat out, and it's so close to the Sun, it has a lot of temperature extremes. Temperatures get up to, in the Sun, 430 degrees. Believe it or not, that's not the hottest place in the solar system. We'll visit that shortly. But also in the shade, or in the side facing away from the Sun, minus 173 Celsius. So it's some real temperature extremes from the very, very cold to the very, very hot, because it doesn't have an atmosphere. Believe it or not, there is ice, water ice, on the poles of Mercury, so close to the Sun. Why? Earth has an axial tilt, about 23.5 degrees. So throughout the relevant season, the summer season for the relevant hemisphere, you've got the poles are facing towards the Sun, so the Sun would essentially gets in there and melts stuff. But Mercury does not have an axial tilt really to speak of. It's sort of, for intensive purposes, straight up and down. So you've got deep craters at the poles, North and South Pole, never gets to see the sunlight. So there's water ice there. And Mercury has no moons. Mercury has a really large iron core. It's about 3/4 of the total mass of the planet. And comparatively, Earth is about 1/3 of Earth's mass is its big iron core in the middle. But Mercury has a large iron core. Two possible reasons. The most commonly or accepted reason over the many, many years has been probably a collision early on after it formed. It had a core, an iron core yay big, with a mantle and a thin crust, and a major collision with another protoplanet or another planet collided with it and sheared off its mantle, and just a little crust formed around the core. That's been the conventional thinking, but some computer studies have recently shown a new possibility, is that when the sun was forming and the protoplanetary disk had formed and so on, the magnetic field lines coming from the sun and throughout the protoplanetary disk were probably a lot stronger close to the sun, where Mercury had formed, in the process of forming, I should say, the process of forming. And of course, magnetic field lines, what do they attract? Iron. So a lot of the iron in the protoplanetary disk and around the sun would have been more attracted towards the region where Mercury was forming, to the point of some planetary scientists will say almost certainly that's the reason for it, not necessarily a collision. The evidence for a collision, there's some very large big basins on Mercury, so there's evidence for both, but a lot of people now are changing their mind on that one. They say, look, I think it's strong magnetic fields, just a lot of iron where Mercury formed.
Sorry, Chris, can I ask a question?
Sure.
Is there a relationship, a formula, distance for the inner planets around the size of the iron cores? I mean, can you determine from that, therefore, Mars and Earth, can you determine that way or not?
I think, I'm unsure, but also you've got a lot of other factors, like Earth's iron core, they think is reasonably good size because of the collision with Theia, the other protoplanetary, to form the moon and so on. So look, I don't know if there's a set pattern. I don't think so, because Mercury stands out on its own as having a huge iron core. It really does stand out on its own proportionally. That's big. 3/4 of the mass is big, unusually big. So I think now, yeah, it could be that they just attracted the iron when it was forming. So let's put Mercury back there. The next planet, Venus, 2/3 of an AU. In other words, about 100 million light years, 100 million kilometres, I should say, kilometres from the sun. So let's have a look at Venus. So this is an image of Venus taken from the Mariner 10 flyby in 1963. And what's your first impression? It's pretty featureless, isn't it? And the reason it looks pretty featureless is because it's covered in thick, opaque clouds, toxic cloud full of sulfuric acid. It's about the size of Earth, and for many years they always called it the Earth's sister planet, but that's where the similarity ends, its size, because of the various features which we'll look in shortly. But yeah, when you first see it like that, it looks very featureless because it's covered in thick cloud cover. It's often known as the evening or the morning star. It often hugs just before, or just after, rather I should say, sunset. You'll often see it as a bright star in the sky, or at sunrise, just before sunrise, you'll see a bright star. And the reason behind that partly is because of that cloud cover. It's close to the sun, so a lot of sunlight hits it. The clouds are great reflectors of light, so it reflects 90% of its light, and we're relatively close to Venus, so we see it really bright in the sky. And because it's inside our orbit, it always appears to hug the sun from our perspective. So you always see it just after sunset or just before sunrise.
Oh, of course, you should mention, if you look at it on a telescope, you'll notice it goes through phases similar to the moon,
Yeah.
which you don't get with the outer planets.
And I think Galileo's first observed that, didn't he? And that was one of his reasonings for saying that we went around the sun. So here's a radar mapping to cut through that cloud, and this was done through NASA's Magellan orbiter, and it's found to have a very young surface. There's been a lot of extensive volcanic activity over the years. So it's got a young sort of lava fields, young surface, somewhere between 300 and 600 million years, which really is sort of almost like a blink of the eyelid geologically time. So a lot of volcanoes and a lot of lava plains. And that there is a computer-generated image of a particular region of the surface of Venus to give you an idea what it would look like. It also has a very thick atmosphere, very thick, mainly carbon dioxide, and it's the carbon dioxide that makes it the greenhouse effect, which makes it, this is the hottest place in the solar system, bar the sun, of course, but in terms of the planetary conditions, 460 degrees. And that's because, yeah, it is close to the sun, yes, but it's not as close as Mercury, but it's hotter than Mercury because of the greenhouse effect with the carbon dioxide. Temperature 460, lead melts at 330. Lead would melt on the surface of Venus. The other thing is, not only would you cook, you get crushed as well. The pressure at the surface is 93 bar. A bar is a unit of atmospheric pressure on Earth at sea level. So we're 1 bar right now. So it's 93 times the pressure. So you'd instantly get cooked and crushed. Most spacecraft only last 1 to 2 hours before all the electronics and various things just get cooked and crushed. And Venus has no moons. Okay, yes, so some other interesting little things about Venus. Its rotation. If you are, of course there's no up or down and north or south really in the big cosmos, but just if you took the solar system and you looked down at it from our perspective, our North Pole, and looked down towards it, all the planets go round the sun anti-clockwise and they all rotate anti-clockwise. But there's one in every crowd, isn't there? Venus. It does what we call retrograde, so it actually rotates the other way around and really, really slowly. To give you an idea how slowly, if you're at the equator, you'd be moving around at a speed of about 6 kilometres per hour. Putting that in perspective, if you're sitting at the equator on Earth, you're zipping around about 1,700 kilometres per hour. So that's real slow. It's rotating backwards and it's rotating real slow. And for that reason, rotating real slow, there's not very strong winds. The air's pretty still. That thick atmosphere is pretty still on Mars. Its rotation, to do a full rotation, in other words, 1 day, 243 Earth days. It's rotating that slowly. To go round the sun, in other words, 1 year, it's 225 Earth days. So a day on Venus is longer than a year. Yeah. You wait a long time for your birthday. So that's just a quirky little thing of Venus. So here's some images, and I try to give you some images here, and we'll do the same with Mars as well. What is it like on the surface to experience with yourself? And the Russians have had 4 landers on Venus, albeit for a short period for obvious reasons. So here's some lovely colour images from Venera in 1982. You can see the front camera and the back camera. And these images, there's 2 things that strike you. One is, notice how the surface, all these little plates, sort of very flat plates of rock, it's lava fields. So once again, very young volcanic lava plain type of terrain, only 300 to 600 million years old, the surface. And the other thing, notice how it's all dimly lit and quite yellow. And that is due to the thick cloud cover. Only 10% of the light actually gets through. 90% gets reflected off. So you get that real yellow hue and dim lighting effect there. So that's what it looks like. So you can go home and tell your family, I know what it's like on Venus. So let's put Venus back there. Of course, the next one you all know, planet Earth. We'll have a very brief look at Earth because we're all pretty familiar with it. So this is an image of Earth taken from Apollo 17 in December 1972 on the way back home again. And it was a journalist who asked one of the Apollo 17 astronauts, took the photo, and said, that's great you brought that home. What did you learn by going to the moon? He said, we learnt that the Earth is fragile, isolated and fragile. And I think that picture really says it all. So we're not really looking after it, are we? I'm sure you've been wondering. 400 million cats on Earth. I looked it up. Those are my 3 cats there. That's Boston. That's Maya, and there's the trouble of all the trouble of trouble, Stella. 8 billion of us, and growing. 70% of the surface is covered with water, which of course gives it that blue marble appearance in space, and also critical for carbon-based life on Earth. We have a nice atmosphere of that 1 bar for our atmospheric pressure at sea level, mainly nitrogen with 21% of the essential oxygen for us. Fossil evidence suggests that life got started on Earth about 4.1 billion years ago. But for over 3 billion years, it would have been all simple, single cellular life, probably in the form of slime, essentially for over 3 billion years. And it wasn't until about 650 odd million years ago that complex life developed. So the take-home message from there, admittedly, it's only a sample of one planet, but it's the only place that we know in the universe with life so far, is that life gets going really quickly, but it takes a lot of time for it to get complex. Our moon, we have one moon, and of course it's the only extraterrestrial object that man has visited, that men themselves have visited, put boots on the ground. Our moon is the largest moon in the solar system in comparison to its host planet. There are other, like Ganymede is larger than the moon, our moon, but its host planet's huge, Jupiter. So proportion-wise, our moon is the largest moon. And we talked about that with the talk on how the moon formed. So let's put Earth there. Let's move on to Mars now. So Mars is at 1.5 astronomical units out, so half as much again. So let's have a look at Mars. This is a lovely image from the Hubble Space Telescope. There's probably 4 things that you can sort of see here that stick out with first impressions. One is the red colour, and that's because of oxidised iron in its soil, in other words, rust. You can see the polar caps with water and carbon dioxide ice in the north and south polar caps. You can see in the southern highlands there, very rocky, these dark areas are here. This is called the southern hemisphere is where all the highlands and the rocky, high mountainous regions are, and that's what you're seeing there, obviously with less red dust on them. But notice here wisps of clouds here and over here, and that's water ice that's condensed on dust particles in the atmosphere. That's what does that. So wisps of cloud in the atmosphere of Mars. Just love that picture. Beautiful. So Mars is about half the size. Diameter-wise, it's about half the size of Earth, as you can see there, which means its surface gravity works out to about 1/3 as you are on Earth, whereby, say, if you're 90 kilograms on Earth, go to Mars, you're only 30 kilograms. I like that idea. Same principle as Mercury, its interior has cooled down. Why? Because it's small, so it's got a relatively large surface to volume ratio. It has cooled down, and it is because of that, it does not have such as a molten core of iron going round and round to generate magnetic field lines around it that protect you from the charged particles coming from the sun. And for that reason, its atmosphere has been partially stripped away. We're going to look at that. So hence the very thin atmosphere. Because it's cooled down, it doesn't have a molten iron core going around, slushing around, creating magnetic fields around it. So very thin atmosphere. 95% of it's carbon dioxide. Of course, oxygen is from life, yeah.
Just to go back to Mercury for a second. Is
there
any magnetic field in Mercury?
Yes. Yes, good question, Dave. Mercury does, because it's large iron core, it does have a magnetic field. It's relatively weak, and it only goes up to 1,000 to 2,000 kilometres. It's weak, but it is sufficient to deflect the lion's share of the solar particles, charged particles. And that's what we'll talk about later is...
So the lack of gravity. The lack of gravity is the causal reason for no atmosphere for Mercury, like you said.
Yes, correct. Yes, yeah, correct. Yeah, it's the lack of atmosphere. Yep, because it does have a global magnetosphere. Yeah, it does. So because atmospheric pressure is less than 1% of Earth's, less than 1%. So it's really, really thin. Because of that, and its extra distance away from the sun, it's really cold. Average temperature on Mars is minus 60 degrees. That's the average temperature. So it's really cold. Why? Thin atmosphere to distance from the sun. It's got 2 moons, and they're interesting. I used to just call them, up to recently they've just thought most likely just captured asteroids, and I've just described them as a couple of potatoes, sort of shaped asteroids that have been captured by Mars. But there's more to the tale. So that Phobos and Deimos are the two. Phobos is the larger of the two, 22 kilometres, so they are relatively small, and yeah, they look like potatoes. Phobos orbits really close to Mars, only about 9,000 kilometres up, and for that reason it orbits about 3 times a day on Mars. And you know what that means? You know how everything rises in the east? Phobos, if you're on Mars, you'll see it rise from the west. You'll see it go over 3 times for the day, all rising from the west, as opposed to rising from the east. Another little concept of astronomy, when anything orbits as such another body, what is the main driver? Gravity. The closer you are to something, the stronger the gravitational force you feel, the faster you're going to go around that larger object. Further out, you're going to go slower. So that's the reason it goes so fast. It's relatively close to Mars, as opposed to Deimos, which is smaller, but it orbits about every 30 hours. A Martian day, which we'll come to shortly, is just a tad longer than Earth. It's very close. So, as I mentioned, up till now, they've thought mainly they captured asteroids. Why? It's because the composition of them was very close to some asteroids, the C-type asteroids, or carbonaceous asteroids, a group of asteroids that have carbon and other things in them, and they've been very, very close in composition. But there's always been a problem with that. The computer studies haven't been able to tie up and work out if they were captured asteroids, they'd be coming in from a certain angle, a certain velocity, and so on, and they couldn't match it up with the nice circular orbits that the 2 moons have around Mars. So there's been a problem, but they thought, okay, we'll just run with it. They're asteroids. Some recent, quite up-close studies of the surface of Phobos have showed 2 interesting features where they've changed their mind now. The surface of Phobos is very porous, so low density. That points more towards a comet than an asteroid. And the second thing is, it's the properties of how it reflects light is very, very close to that of a series of comets called Jupiter family comets. Jupiter family comets are comets that, as they go around the sun, instead of going way back out to that Kuiper belt, the Kuiper belt objects, belt of small rocks, it only just goes out a little bit past Jupiter. They're mainly captured and under the influence of Jupiter's gravity, so they're called Jupiter family comets. And the properties on Phobos' surface is more in keeping with these Jupiter family comets, so I think most likely that's where they came from. And there's actually speculation that the 2 once joined together as a bilobular object and as one comet, and as it got close to Mars, it got captured and also just pulled apart. The 2 lobes got pulled apart. So that's the current thinking of how Mars got its 2 moons. Let's just have a look at some Martian landscapes once again, so you can think, I know what Mars looks like. So this is a lovely little view here taken by the Curiosity rover. And 5 rovers on Mars, 2 still operating, one of which is Curiosity. And this is Dingo Gap and Gale Crater. So Gale Crater is the main crater which Curiosity landed in. They thought it was once to have been a big lake. And right at the foot of a Mount Sharp, a big mountain sitting here, bang in the middle of it here. So these distant mountains, what you see hills or mountains here, are the rims of the crater. So this was all once full of water. And the main features that strike you here, the 4 main features are, once again, the red soil. Look how red it is, because of the rust in the soil. Look at the rocks, how eroded they are from wind and water, flowing water. They're all smooth and worn out, aren't they? So the erosion there. I love this, the tracks, that us humans, we've left our mark on a planet. I love that, sort of just the tracks on the Martian soil. The other one, look at the sky. It looks very pale, doesn't it? It's not that rich blue, and that's because it's very low atmospheric pressure. It's not much atmosphere there, less than 1% of Earth, so you haven't got so much atmospheric particles reflecting light. Yeah, making that blue colour. Another one, I just love looking at these images. I'm being a bit selfish. I put them up so I could see them on the big screen too. This is from the other rover that's still working, Perseverance, and this is in Jezero crater. Once again, thought to be a lovely big lake at one stage, but you can see some mountains here. They're about 2 kilometres away, but look here at these rocks, how worn they are, just from erosion, from water and wind. Beautiful view, isn't it? Beautiful. And of course...
Is that true, Colour? Is that how it really would look?
Yeah, I believe so, yeah. And once again, the pale sky too, yeah. That's what it thought to look like about 3.5 billion years ago, what it probably looked like. Nice big crater here forming a lake. You've got water flowing in here. And you can see with, I could put pictures here all day, but you could see here the crater today, there's all this big delta of material as it flooded into the base of the lake, and then you can see water flowing out through here as well. So that's quite cool. The largest volcano in the solar system is on Mars, Olympus Mons. And this is, a scaled artist impression. You can see Mount Everest. We think we're pretty cool on Earth with our Mount Everest. It's about 8.8 kilometres high. You're looking at 25 kilometres high for Olympus Mons, 3 times the height as Everest. You think, wow, how come? 3 reasons. One is Mars has experienced a lot of volcanic activity over the eons. It's also because it's low gravity. The surface gravity is 1/3 of Earth, so naturally rocks can build up higher and higher. You've got less gravity trying to pull them down, so things can stack themselves up higher. And the other thing is it does not have tectonic plates. So instead of a series of plates that under a certain weight of a massive big mountain that possibly could start sinking, Mars is a one-plate planet. Just one rigid plate. In other words, it's got stability. It can prop up a heavy mountain a lot easier without sinking. So those 3 reasons why you'll find the largest mountain in the solar system. That's a little quiz take home for the family up. You don't need to give them chocolate though. So this is sunset on Mars. Because notice how small the sun looks, and look how dim it is because it's been further away. But notice the sky sort of looks like a blue-grey sunset instead of the red. Once again, less atmosphere and so on, less particles to scatter light. You just don't get the sort of nice colours that you get here. As I mentioned, one sol, which is the term used for a Martian day, is 24 hours, 40 minutes, just a little bit longer. Mars orbits the Sun every 2 years. It's sitting further out at 1.5 astronomical units from the Sun. It orbits every 2 years, and which means it has 6 monthly seasons. What causes seasons? The axial tilt. And Mars has got a very similar axial tilt, tilted up on its side, so it's very similar to Earth's. So its seasons are 6 monthly instead of 3 monthly. So let's put Mars back there. Jupiter's next, the king of the planets. And Jupiter sits out at 5 astronomical units. You can see where this is heading straight away too, can't you? Not only have you got this dichotomy in the sizes of the planets here, but look how all crunched up and close together they are. And suddenly you'll see here we're starting to move, getting bigger and bigger distances. So there's Jupiter. This is another image taken by the Hubble Space Telescope. Beautiful. Diameter-wise, Jupiter's 11 times the size of Earth. Volume-wise, you'll fit 1,300 Earths in size Jupiter, volume-wise. It orbits because it's further out. So there's 2 things going on there. It takes 12 years. Why does it take so long? A, because you are further out, so your circumference is a lot bigger. You've got more distance to travel. But also, you're that much further away from the Sun. So even though Jupiter is large, and of course the gravitational force you allow for both masses, but still that distance way out more than compensates for Jupiter's size. So it's the gravitational force, the drive in the orbit's a lot less, and you're much further out. So it takes 12 years. So that's the reason behind that. 1 day is only 10 hours. It rotates really quickly, which means it has a lot of winds. Now you might say, why? Why does it rotate quickly? And that's all to do with the principle of conservation of angular momentum. And that is whenever something contracts down, if it's rotating and contracting in, things start going faster and faster. And a classical analogy is your ice skating person. They've got their arms out, they're skating around so fast, and you watch them, they bring their arms in and they start rotating a lot quicker. And most of the planets, or they say the inner planets up till now, they've been gathering rock and rubble from a certain distance out, and gravity slowly bringing it together. But Jupiter suddenly is full of hydrogen and helium, the gases, and it gathered that hydrogen and helium from huge distances out. So you had proportionally a massive big sphere of collapsing hydrogen and helium coming down to form the gas giant, which means it just started getting faster and faster and faster and faster. It had a lot of contraction to come down to that planet, and that explains why Jupiter is just spinning so fast. It's all from the large distance that it captured all its gas, and which also infers it has high-speed winds. It's a pretty violent place. So, yeah, as I mentioned, it's a gas giant, so it's predominantly hydrogen and helium. We're going to talk about that later on. 98% of the universe is hydrogen and helium. It's got these prominent bands. You'll probably, if you've seen it through with your own eyes through a telescope, you can see all these zones and bands here, and that represents winds of different temperature and composition. The white butts are called zones, and that's rising. That's a lot of ammonia, and it's sort of rising, so it's warm, rising air, and it causes these white zones. The reddish-brown stripes are known as belts, and they are down at lower altitudes, and a lot of ammonia hydrazide, and various few other little chemicals going on in there involving ammonia and hydrogen. Its atmosphere is very thin because it's just hydrogen and helium, and it just goes out, but it doesn't have a hard surface because it's a gas giant. So there's no hard surface. You don't just go through the atmosphere and bang. It just the pressure gets more and more, and you'd get crushed. Its core is actually metallic, is solid. It's metallic hydrogen, but you'd be crushed well before you got even near there because of the pressure. So there's no real hard surface to speak of. Its red spot is another little feature that everyone is familiar with Jupiter. So let's have a little bit of a close-up look at that. That's thought to be a big 400-year-old storm. There's the size, it's larger than the size of Earth. And there's evidence to suggest, looking back through previous images of it, that it may not be the same storm. There's a storm going on there, but it may not be the same storm that was going on there, say, 100 or 200 years ago. So that's an idea that's been put forward recently. So Jupiter has 91 moons. Most of them are all probably just captured asteroids and comets as they've gone past, and Jupiter's so large it just captures them and pulls them in, and they become a moon. But 4 of them are known as the 4 Galilean moons, and they all line up in a nice disk here. And they probably formed just as the sun, as it was contracting down and going faster and faster, formed that nice protoplanetary disk that the planets formed from. On a lesser, smaller scale, probably the same happened when Jupiter was forming. You had all that gas and dust was all coming down, condensing down. It was spinning faster and faster, and a little protoplanetary or proto-moon, circumplanetary is probably a better word to use, circumplanetary disk formed, and the moons probably formed from there. Now, they're interesting, these moons, and I've just highlighted 2 of them here. First one is Io, the closest most moon. This is the most volcanic body in the solar system, at Io. And you're probably thinking, whoa, volcanism. That involves heat, doesn't it? Geological activity, heat down below that's coming up and spitting out magma and all sorts of volatile chemicals and materials and so on. What is that going on so far out from the sun? Isn't it meant to be cold out there? It is very, very cold out there in the environment around Jupiter. But there's a process going on here, which is another important principle, which I'm going to come to shortly. And involves resonance of the orbits of the moon. I'm going to come to it. I'm just going to show you this in the next moon, Europa, and then we'll talk more about it. But needless to say, it involves a lot of gravitational pull and tugging, like a tug of war between Jupiter and the other moons, the other Galilean moons, that squeeze and stretch it and create heat inside it. And we'll talk about this a little bit more shortly. But that explains why, there you go, the most geologically, volcanically active region in the solar system is way out in the cold. The other moon to mention here, which we're going to talk about, is Europa, and it's covered with an ice, a water ice crust with various cracks and ridges all over it all, which suggests that it's a crust of water ice, but there's a subsurface ocean going on underneath, like here. So here's your crust, here's your ocean. They even think there's hydro vents possibly going on underneath here, the heat that's causing tidal currents, which causes all these cracks and ridges going on. It's thought to be salt water there, and there's a mission now heading out to have a closer look, because what do we know about how life got started on Earth? That's still an area of research, but one of the very credible lines of thought is that it originated from hydrothermal vents in the bottom of oceans on Earth, because there's lots of minerals down there, you've got energy, you've got water, the conditions would be ideal for life to get going. And certainly around the hydrothermal vents today, in deep ocean trenches and so on, they're full of life, all sorts of microorganisms, microbes that can quite happily thrive in those conditions. So it's a candidate for another place where there could be life in the solar system. So those are the two interesting moons of Jupiter I just wanted to mention. Let's move on now to this whole concept of what's driving that. Once again, it's so far out. Why you got these hydrothermal vents going on? Isn't that mean there's heat going on? Absolutely. So this is the concept here of orbital resonance, whereby, let's start with, so here's Io, Europa, and Ganymede. There's three of the moons. There's a fourth moon, Callisto, but that doesn't really participate in this. It's called orbital resonance, where as Io goes around a lot quicker, remember it goes around quicker because it's closer. For every one orbit of Io, you've got here Europa, that's lined up with it, but just on the other side. And then 2 orbits later of Io, you've got Europa back directly in line with it, beside it, and you've got Ganymede over here. And then 4 orbits later, you've got all 3 back lined up, just like that. And they all gravitationally tug and pull on one another. And what's happening with this arrangement is that you've got, of course, in the middle, you've got Jupiter, the largest planet by far in the solar system. It has got huge gravitational pull on Io and Europa. And it's trying to make their orbits nice and close and circular. Meanwhile, you've got a regular tugging and pulling on all these moons, tug and pull each other, trying to stretch them out a little bit into more elliptical orbits. And it's that constant tug of war that's constantly stretching and squeezing, compressing the interiors of these moons. More so Io, a little bit less Europa, and a little bit less Ganymede. But it's, in a good analogy, is you get a paper clip, bend it backwards and forwards. It gets hot, doesn't it? And it's the same process going on here. The interiors of these moons get hot because of this whole concept of orbital resonance, where the moons are constantly and regularly lining themselves up and create a tug of war between that and Jupiter. Yeah, Liz? Callisto's further out, I mentioned that. Yeah, Callisto is the next one out here, and it doesn't participate so much in the orbital resonance. It's not geologically active here. So I just wanted to mention these 3 here to keep it straightforward, and in particular the two feature moons for tonight around Jupiter. So I've got this little GIF file here. I tried slowing it down, but I couldn't, so it runs a bit quick, but you'll see that they flash lights when they line themselves up. I wish I could slow that down. But you can see them regularly lining up. You see the lights flash when it does that. So that's what called orbital resonance, and every time they regularly line themselves up, they pull and stretch like a tug of war, stretching, squeezing, compressing, and it's like a bit of plasticine, and it just heats it up, and that's why in that cold environment around Jupiter, those 2 moons are geologically active. In fact, all 3 are geologically active, just more so in Io, and then Europa, and then Ganymede. So let's put Jupiter there. Let's move out to Saturn. And suddenly you're doubling the size of the solar system. You're going out to 10 astronomical units now for Saturn. There it is here. This is an image taken by Cassini, NASA's Cassini spacecraft in 2008. And the first thing that strikes you, everyone's sort of, what it's famous for is its rings and its colour. It's got a yellow sort of colour. It's got some hydrocarbons in its atmosphere. Its atmosphere, once again, like Jupiter, 98% of the universe is hydrogen and helium. So it's predominantly hydrogen and helium, but it's got some hydrocarbons in the atmosphere, and it gives it that yellow-brown sort of colour. It's got a very low density. Its density is less than that of water. So if you had a body of water big enough, Saturn would float in it. It's lighter than water. And of course, prominent ring system, which everyone likes to talk about and know about. It's really fragments of rock, ice and dust, just millions and millions of them around there. How did it come about? The most likely explanation is that a moon got too close to Saturn. Within it reached its what we call Roche limit. A Roche limit is the region around a planet, and the bigger the planet, the bigger the region, whereby the gravitational forces on anything that gets inside that are so great, it'll start just ripping that object apart. And it all depends on, the Roche limit, the size of it, depends on the size of the object that's getting close to it as well. So if you get an object whereby it's small enough, whereby its mass is not big enough to hold it together, within the Roche limit of that planet, the tidal forces will just slowly rip it apart. That's probably what's happened here. They estimate these rings they have not been there forever. They've only been there for about 400 million years. Yeah. How do they know that? They estimate the amount of dust that's fallen on, not the lint dust like that, but cosmic dust, just little bits of fine gravel, if you will, gristle gravel that's floating around out there that's settled on the rocks. And they study the rate at which that accumulates, observe what you got there. And from that, they estimate it's about 400 million years old. And they've estimated it'll probably all disperse or work its way in towards Saturn over the next few million years, next few hundreds of million years. It won't be there. And then you might get another moon that does it. So interesting, but by no means permanent. So Saturn takes the medal for the number of moons, 146 moons. There's two of special interest that I just wanted to highlight tonight. They're all interesting, but there's just two that I wanted to highlight tonight. First one is Titan. This is an image from Cassini, and Titan is the only moon in the solar system with an appreciable atmosphere. So it's got a hazy atmosphere. You'll see all this big sort of opaque haziness. That's because of carbohydrates. It's mainly nitrogen, but it's got a lot of hydrocarbons in its atmosphere, and that causes this hazy appearance. The surface pressure is 1.5 bar. In other words, 1.5 times the atmospheric pressure on Earth at sea level. That's the pressure you would experience on the surface of Titan. Titan, and I won't go too deep into this because Jonathan Park, I think, is talking about this next month. But a Titan has got rivers and streams and lakes but not water, but liquid methane and liquid ethane. So it's just another little surface. So it's far from being just a boring old cratered moon. No, it's interesting. It's got the only moon with appreciable atmosphere, with 1.5 atmospheric pressure. So a decent atmosphere, and it's got lakes and rivers and so on as well, but just not water. The other one I wanted to highlight was Enceladus, another interesting moon of the solar system that belongs to Saturn. And just like Europa, it's covered in a crust of water ice. And you see all these, they call them tiger marks, all these ridges and cracks through here. Once again, that is evidence there's most likely a subsurface ocean underneath. I think it's salt water. But also you see all these plumes, all these jets of water vapor and ice. Cassini flew through those plumes, analysed them, just with the instruments that it did have. It didn't have, I should say, past tense, have instruments looking for life and stuff, but it had instruments that picked up those organic compounds amongst all those plumes in there. So the general consensus is there's a subsurface ocean also of salt water with a lot of these warm, hot water getting through these hydrothermal vents going through here, once again with minerals and stuff. And you might say, okay, there must be, you'd quite rightly deduce, there must be an orbital resonance going on, and there is with the moon Dione. So that's causing orbital resonance, same principle as the moons around Jupiter. So that is another place that they're going to look for life. So those three, Io's too rough. You're not going to get any life there with all that volcanic activity. But you've got Europa, you've got Titan, and you've got Enceladus are all candidates to go looking for other places where possibly there could be life in the solar system. Pretty amazing, isn't it? So far out. Next one is Uranus. Uranus, once again, you're doubling again. Look at the big distance you're going out. 20 astronomical units. That's Uranus there. It looks pretty featureless, doesn't it? And that's about 4 times the size of Earth. It's a large, what they call ice giant. So it's full of, got water ice, ammonia and methane ice as well. That's covering its surface. It's got a very thin atmosphere, hydrogen, helium, once again, 98% of the universe, hydrogen, helium, predominantly hydrogen, helium with a little bit of methane, and it's the methane that gives it its blue hue that you see here, that very bluish, greenish hue. That's because of the methane. This is a lovely image from the Keck in near infrared, and you can see 2 things here. One is you can see it's got a nice little ring system that you can only see in infrared. So just like Saturn, and Jupiter's got a ring system as well. I put in there those big planets have ring systems there. But the other thing you'll notice, it's tilted right up onto its side. How did it get like that? Probably a collision early in the formation of the solar system when it was very, very young. Another major body collided with it. It was a pretty violent place. And I didn't mention, why is Venus, the odd one out in terms of the retrograde and really slow rotation? Probably a large collision during its formation process early in the solar system. It was a pretty violent place. Look at the surface of the moon. Look at the surface of Mercury. So that's quite cool. Now it's got 28 moons. Most of them probably captured smaller objects, but 5 of a reasonable size. And they're all named, all the moons of Uranus are named after characters from William Shakespeare and Alexander Pope's plays. Just a little bit of trivia, yeah. And my favourite one is Miranda. I think Miranda was at The Tempest. Miranda, did you know the Shakespeare? I think it was The Tempest. Macbeth and Hamlet were my favourites. But and why did I like Miranda? It's quite cool. It's got the largest cliff in the solar system is on Miranda, Verona Rupus. It's 20 kilometres high, this cliff, largest cliff in the solar system, 20 kilometres. Whereby if you jumped off it, it would take you 12 minutes to get to the bottom. So you'd have 12 minutes to do a few selfies and put on social media and stuff, put on your Facebook page or whatever. But the sad news is when that 12 minutes is up, you're going to hit the floor at 200 kilometres per hour. So you won't get to see many of the comments and who liked it and who didn't like it. So there you go. That's just an interesting...
What if you had a parachute?
No, there's no atmosphere, so that wouldn't do you any good.
Oh.
It's all over, baby. You're going down.
What if you you'd only have to have a ship or something and you have to thrust it? Would that work?
Yeah, well, yeah, you'd fly over it, of course, but we'd say hypothetically, if you...
But you
yeah.
get thrust as you came to the bottom.
Yeah. Okay, so that's Uranus. Let's move on to Neptune. 30 astronomical units. See how the spacing is getting more and more. So this is the scale. That's the scale. So there we go. Let's have a look at Neptune. And this is a picture taken in 1989 from Voyager 2, NASA's craft that went out to the outer solar system. As you can see, it's pretty featureless. One orbit, 165 years. So it's 4 times the size of Earth, so very similar to Uranus. Very similar once again to Uranus, a very large ice giant. It's got ices of water, methane and ammonia ice. Thin atmosphere again, the hydrogen, helium going on with some methane. And the initial impression was they had images of these, a richer, deep, a darker blue than the blue-green that you had Uranus. And it was thought that was probably from a lot of the high winds going on, quite sort of a lot of windstorms going on in Neptune, stirring the methane up. But some more recent images suggest that actually that might have been a false colour going on here, that it's probably a very similar colour to Uranus. 14 moons, one particular larger one called Triton. There you go, just what we need to mention there. Okay, so that's the planets in a nutshell, and you can definitely see here this dichotomy, so to speak. these two, let's just bring them up. I think I have them here. We're starting with the rocky ones, which makes sense. These are your 4 inner planets. They're significantly closer to the sun. They're small, they're dense, they've got solid surfaces, and they're dominated by your rocks, like your silicates and so on, your silicon and your oxygen compounds. Then you've got these 4 outer, more spatially spread out gas giants, gas and ice giants, much further out, very large, low density, ill-defined surfaces, and they're dominated by the hydrogen, helium gases and the ices of water, methane and ammonia. So that's your dichotomy that's going on there. So that's the end of our visual tour, chapter 1 of the solar systems. I hope you've enjoyed that, and you now know you've got a few images in your mind what it's like on the surface, a little bit about the moons and so on, some interesting moons. Let's look at the next one. Let's look at some reasons to explain the dichotomy of the sizes. There's 2 prime reasons, but there's a third reason that has a contributory factor, which is just interesting food for thought. One is we're going to go through each of these, but just listing them first. The universal abundance of elements, the inner regions of that protoplanetary disk being too hot for ices, and we're going to talk about the concept of planetary migration. So let's look at universal abundance of elements. As I've previously mentioned, so this is right across the universe, 98% of the universe is hydrogen and helium gas. About 2%, let's put that up here, and of course there's extreme amounts of it to make up the gases for the gas giants. You're probably already seeing where this is starting to head. Carbon, oxygen and nitrogen, the materials that combine, that react with hydrogen to form water ice, as in hydrogen, oxygen, H2O. Carbon and hydrogen, that's your methane, and your nitrogen and your hydrogen, that's your ammonia. Those 3 elements that to form your ices are about 2% of the universal abundance of elements. And then just a tiny amount of your silicon and your iron, your magnesium and so on that go to make up your rocks. So that's the universal abundance of elements. So the things that go to make up those gas giants, there's just oodles of. There's plenty of material for ice to make up your ice giants, but much less, of course, and only small amounts of the material to go make up those rocky planets. So that's one good reason. You can see the logic behind that. Less material, so they're going to be smaller. So that's one reason for the dichotomy. Another reason involves this protoplanetary disk, and here's an artist's impression. Here's the young sun forming here, and this massive big disk, protoplanetary disk, or circumstellar disk, if you will, call it what you like there. And you'll see here, he's also drawn in the disk here, what we call a temperature gradient. And it makes sense, doesn't it? How it's going to be hotter, a lot closer. There's going to be a temperature gradient. It's going to be hotter the further you get in towards the sun, and cooler as you get out. That just sort of makes sense because that's your heat source in here. The bottom line is the whole lot gets so hot such that all the material here vaporizes into gas form. And then as the whole thing cools down, you start getting materials condensing into their solid state. And here's this temperature gradient. When things start condensing out, you get this temperature gradient where sort of so close here, it's about 2,000 degrees. And the only thing that can condense out here is all your materials that go to make up your metal and your rocks. They're the only things that can condense out of this disk at this stage because it's just so hot. As you go out, you get cooler and cooler, and suddenly you get to a certain position in the disk where it's about 0 degrees Celsius. So you've got your water ice can start condensing out. They call it the ice line because suddenly your ices can start condensing out. And out here is your water ice. And then a little bit further out, you've got your methane and your ammonia ices. They can start condensing out as well. So, because here's the catch, as I've described, different materials condense out to solids at different temperatures. So it makes sense. You're going to get metals and rocks right throughout here, but anything out here, you're not going to get any of your ices until out here. And what happens is they've all got their nice little rocky centre, all the planets, the whole way through. Your ices form here, and then as you get out to a certain point, you've got enough ice whereby you reach a critical mass enough to start pulling in all the gas, the hydrogen, helium around you. And of course, there's 98% of the whole deal is hydrogen and helium. So you just got oodles off it, and you get these massive, so you get pretty large ice giants. So you get small rocky planets, pretty large ice giants, but you get these big massive gas giants. And that's the reason why, because of the temperature gradient combined with the universal abundance of elements concept. So there's some little concepts in astronomy for you, which the whole idea of these Introduction to Astronomy talks is about. An interesting topic, using it as a vehicle. Now, here's something else that would have contributed towards what we see today with these small rocky planets, planetary migration. And these are the questions here. Just why isn't Mars bigger? It's further out in that protoplanetary disk than Earth, so where there's more material. So you would expect it to be larger than Earth, but it's not. It's half the size, diameter-wise. Why isn't Earth bigger? As I mentioned, these super Earths, as far as exoplanets, planets in other star system and planetary systems, are quite common. We don't see any in our solar system. We just got one Earth. And why is there an asteroid belt where there should be a planet? Why have we got this ring of rubble when there should be an asteroid, when there should be perhaps a planet sitting there? So these are some interesting questions that this helps to answer. Enter the grand tack hypothesis. And it goes by whereby, and this is all done with computer models and so on, there's two main points here, is that the four outer planets, when they originally formed, they were much closer than they are now, and they were in more circular orbits. And the other principle or concept is that Jupiter and Saturn formed first. Jupiter very, very first, because why? It had just had more mass coming together, more gravitational attraction, and it just got going a lot quicker. It fully formed within about 10 million years. It got up running really, really early. Saturn was formed quickly as well, but not quite that fast, but did get up running fast. Jupiter was formed at about 3.5 astronomical units from the Sun, so a lot closer. Remember, it's about 5 actually, it's about 4 point something, it's close enough. It's roughly about 5 astronomical units now, it's further out, but it probably formed about 3.5 astronomical units away from the Sun. And as it went round, it started moving, spiralling inwards. Why? Because of the gas drag effect. You know, the other planets hadn't formed, they were in the process of forming, so there would have been a lot of gas and dust and material in its way. So it created a drag. So it started slowing down a bit and started spiraling inwards. It's easier now just to start talking this way. So it formed here. Here's the Sun, and it started, because of that drag, started losing its orbit and migrating inwards. At this stage, Saturn was starting to form at the same time and going through the same process. Jupiter moving inwards, spiraling inwards. Saturn then started doing the same as well, because it formed early, still a lot of gas and dust and debris and carry on within the disk where they're moving. So they're getting some drag effects, starting to slow down, starting to migrate inwards. Jupiter migrated right up to 1.5 astronomical units. What sits there today? Mars. Yeah, Mars sits there. So it went right into where Mars was in the process of forming. Remember, Jupiter and Saturn formed first. So Mars was still in its early days trying to get itself formed. In strolls Jupiter onto its turf, scatters all that material in that region, scatters it into the inner solar system, and really causes havoc. Clears a lot of material out of the inner solar system, causes a lot of chaos, which means less material available for those inner planets. Jupiter cleared a lot of that material out because it was there. So it affected Mars the most because it sat where Mars was trying to form. So that would explain why Mars is just a little runt, only when it should be a lot bigger. It would also explain why Earth is the size it is and not the size of a super Earth that are so common in the population of exoplanets. And it also would have prevented a planet from forming in that asteroid belt because it would have gone through there and scattered it. Now you might say, what stopped it from stopping there? Because remember, a lot of these exoplanetary and these planetary systems, other planetary systems with exoplanets around other host stars. Remember, there's a lot of hot Jupiters we see. So obviously in some systems, these Jupiters just keep going. and end up as hot Jupiters, being really, really close. But fortunately for Saturn, saved the day. And Saturn started migrating closer and behind it as well, till it developed another one of these orbital resonances. So what we call a 3-to-2 orbital resonance, Saturn formed with Jupiter. So for every 3 orbits around the Sun, Saturn did 2, because it was going slower. And it formed a resonance, and it held on, and that resonance locked Jupiter in place. And then slowly, it's a little bit complicated, but the combined gravitational force of Jupiter and Saturn acting as one together in that orbital resonance then started putting created a torque effect and started disrupting the angular momentum of the planetary disk, protoplanetary disk there, and started creating a force, and they started going back outwards again. So Jupiter only got as far as 1.5 astronomical units. So it caused a lot of chaos. As it went back, it did some more scattering of the asteroid belt. So that's why we didn't get a planet there, because Jupiter ploughed through that area twice. Jupiter sat for a while at 1.5 astronomical units, so it really booted most of the material out that Mars's fate was sealed as soon as Jupiter started heading inward. And it disrupted a lot of material that would have helped form a bigger Earth, but not as much as Mars. So it explains all of that. So Saturn and then Jupiter in there started moving back outwards again. Both moved much further out. Jupiter to about where it sits now, about 5.2 astronomical units, and Saturn to about 7, which later went out further. So that's called the grand tack. You've probably heard of the Nice model before, and that just carries on beautifully. The two theories complement each other quite nicely. And that is, the story doesn't end there, is that then Jupiter and Saturn, them moving out, then formed a 2-to-1 resonance. So the resonance was changed. For every 2 orbits of Jupiter, Saturn had 1 orbit around it. And that resonance upset the orbital orientation, in particular, made the orbits of Uranus and Neptune, it threw them out, how elliptical their orbits were, threw that out, and all 4 planets just caused chaos. They moved out further again. Uranus and Neptune swapped places. It used to go Neptune-Uranus. They swapped over. Neptune kept on ploughing further out and really caused havoc with all the protoplanetary disk material. That's where the Kuiper belt is today, and just created that big pile of rubble in there as well. And remember, I talked about the late heavy bombardment stage. That's when the planets had formed, but in the next 500 odd million years, they were bombarded with material coming from the outer solar system to the inner solar system, causing all that craters on the Moon and the craters on Mercury. That's thanks to Neptune ploughing all out there. So it all ties in beautifully. And this is all done with computer simulations. So that gives you 2 planetary groups. So what you see today in the solar system, how things are, is from the universal abundance of elements. 98% is hydrogen, helium, about 2% of the material that go to make up the ices, and only a tiny amount that make up the rocks and metals. The protoplanetary disk temperature gradient, in other words, that disk around the early sun where the planets were going to form, as they started condensing out, you had that temperature gradient, really, really hot, too hot for ices in the inner proportions. But so that's why you get all the ices forming further out. And that early planetary migration of the outer planets, in particular, Jupiter getting the drag effects. It was up and early, so it had a lot of debris still around it, started moving inwards right up to where Mars was trying to form. Saturn saved the day by forming a resonance, and the 2 of them moved back out again. And of course, we talked about what we see, the geothermal activity that's going on in these outer moons, in these cold environments. Why? Because we've learnt today about the concept of orbital resonance of Jupiter's and Saturn's moons, creating a tug of war, tidal forces between the planet and the other moons, stretching and flexing and compressing the interiors of those moons, creating heat, creating all these lovely volcanic activities, ice surfaces, subsurface oceans and hydrothermal vents, and possible places for life. And I hope you've enjoyed planets and moons of the solar system through modern eyes. Thank you very much. We can take any questions. I'll just briefly mention first is next month's talk is going to be Jonathan Parker's coming up from Hamilton, and he's going to continue on from this, talking about some interesting, quirky little surprises with the solar system. So today I've just really thrown the ball up, and he's going to come along next month and smash it over the net. So a bit of fun. So any questions related to tonight? Yeah.
Just in relation to the gas giants, are they still moving outwards? Or
No, they're reasonably stable. They're stable now, so it's okay. You can sleep tonight. They're stable. Don't you worry. Yep. Otherwise, no, we're all good, guys.